And I should in advance excuse, my voice is for some reason very bad this week, so it might be in the worst case that I just fail to speak at some point and then I should stop. Yeah? At the moment it seems that I can speak loud enough for this room. To summarize what we did last time, we are in the chapter on globalization, which I think I wrote wrongly. It's chapter 9 because we started to add some chapter in the meantime, right? So in the video I think it said 8, but yeah. So we are in chapter 9 and we were in section 9.3 where we have proven a global convergence of one method, namely of the AMIO backtracking method. Before we did that, I just want to recall a few things that we have presented last lecture, namely, we remember there are basically two methods that we have learned how to do line search. One was AMIO and backtracking. This algorithm was already known before, but the second possibility was to use the Wolfe conditions. And the Wolfe conditions were a second set of conditions that should be satisfied by a step in order to be able to prove global convergence. And these Wolfe conditions are actually similar. The first one, it was one condition and another condition, right? And the first one was actually AMIO, but it's called then the first Wolfe condition because this guy invented it independently. And so this is the first one is AMIO or the first Wolfe condition. Yeah. So I will not repeat that one, but then there was the second one, which was a second Wolfe and which was a curvature condition. And this curvature condition was like before the backtracking, it was ensuring that the steps cannot become too short, and it was somehow ensuring that we would, compared to the slope that we had at the beginning, would have that we find a point where the slope is already going up. And so one thing I should mention here is that you need a different line search than backtracking. So you cannot do it with backtracking, but you have to first, you have to be able to even make the step larger than 1. Yeah. TK bigger than 1 is possible. It's actually, there might be situations where you don't find a Wolfe point in the interval between 0 and 1, but you need to go further. And the reason for this was technical, and I mean, we didn't want to go too deeply into these Wolfe conditions, but they can be useful and interesting, and the intuition, as I said, at some point, so you have, maybe I draw already this interesting other picture, so we have here, for example, our starting point. We have a slope which is negative, but then the AMIO slope would be less negative. That is the AMIO slope. Everything below is satisfying the AMIO condition. But then the Wolfe condition was taking one slope in between these two things and say, I want a point that is in the slope. So this one is a line that I can move up and down, where the slope is bigger than this. So the slope should be between this and this. And that's only satisfied, I mean, this slope you see from here on. Before there was always a stronger negative slope, but from here on the slope goes up, and I think every point from here to here satisfies both Wolfe conditions. And it always exists because of the fact that if this point exists, right, because your function, the AMIO function goes down, but your function itself is bounded, but it might exist only when you go far away. So t equal 1 might be here, for example, and then you need to go further in order to find even this point. And then we know, because this point exists, and the function in between is smooth, there exists also one point in between this point and this point, where the slope is exactly the AMIO slope. And because this function needs to go up, because all points here, it must be a point, sorry, yeah, there exists a point that is first of all. So we should always first find the first point where the Amio condition is getting to be violated, and that's this point. So we exclude the fact that it's going up and down, so we need to have this first point. And for this first point, we know that the function is always below the Amio line. There will be one point where the Amio slope is taken, which is actually this point. That's the Amio slope. And the second Wolfe condition says the slope should be bigger than something which is even less restrictive. So this point already, which is parallel to that, already satisfies the second Wolfe condition. And all points from here on satisfy it. So it's any point on this interval that satisfies the second Wolfe condition. There was a strong version which would say also upwards slopes are forbidden, so then we allow only these points. But these Wolfe conditions need a different line search, and it's a bit more complicated, and I should say that the typical way to do it is first of all find a point that violates the Amio condition so that you have something on that side, because then you know the right point must be somewhere in between, and then you could divide your interval and then evaluate your function in the middle of that point, evaluate the function and the slope, and then you can check Amio and first Wolfe and second Wolfe, and based on the result you can then decide if there must exist a Wolfe point on the right or on the left side of this interval, and based on this reasoning you do interval refinement until you have found such a point. That would be one way. There are different ways of line search. But the main message I wanted to say is Amio can be done just with backtracking, or you can do the Wolfe conditions with a different line search. We only implemented Amio and backtracking, and we also only proved convergence for Amio and backtracking, but you can prove convergence using these two Wolfe conditions, and that's it. So the concept of this lecture is to present you a few more methods than what we really actually prove. So, as I said, for Amio and backtracking we have proven global convergence. For many other methods that I will present, we can prove it similarly, but we don't, because it will be technical. And you get the spirit already from one. So what I want to do today is I want to introduce another method for globalization. These are both line search. So both of them are called line search methods. And an alternative way for globalization is called a trust region method, and also this can be in many flavors, but the basic idea is always the same, and the basic idea is what I want to explain. So if you recall what we did in line search, the basic concept here was that we have an iterate xk plus 1 that we get from an old xk plus some step that we could compute from minimizing a quadratic model, and then the step was multiplied with a factor t, and this t was actually the line search parameter, the step length. So trust region methods, so the basic reasoning behind this was that sometimes your model is somehow bad, so you need to make shorter steps to make sure that you always go down. For trust region methods, the reasoning is a bit different, and what trust region methods do is actually they iterate always by with a full step, so to say, but the way they generate this full step is modified so that the steps get small enough if necessary. So they make these steps smaller, but not necessarily on by just shrinking them, by scaling them down, but by turning them. So the image that you should have in mind for line search is when you are in a multi-dimensional space and you have your current iteration somewhere, then your full step is somewhere here, and then you possibly do a shorter step. That's what line search does. First, determine the direction. Second, you look how short do you need to make your step. What the trust region method does, it says also I have here my landscape of optimization, and I have somewhere a point. And what I know is that I have my first derivative of this point, so I should actually, in the neighborhood of my point, I should have a good model. But I want to make big steps, of course, and then if you try a big step and then this big step is somehow here, and it turns out that this is going upwards and it's just much too big as a step, then you say, okay, then I don't trust my model anymore, so the region of trust should be reduced. And then you say, maybe I trust my model only in a small region, and then let's try to find the best point that minimizes my model in this region. But that might not necessarily be the point that is here, but it could be, for example, here, depending on what the gradient is. And later on you could say this is still not giving you enough, and then maybe your model will be minimal on that point. So you might sometimes decide to not do a step, so you will actually sometimes do, so to say, null steps. But what you will do is you will adapt, if necessary, the size of a trust region radius, which we call, in this literature, we call this actually typically delta. It's just the delta. It's not the it's not a differential operator, but it's just one number. It's a scalar number, delta. And it can be with an index, delta k. That's the radius that we have at iteration k. And the pk we get from a trust region method. And it comes from an approximate solution, I should also say, of the so-called trust region. TR is always for trust region, so I will not write it again and again, so I just say it once. Trust region is the solution of a trust region subproblem. And this subproblem is similar to the one that we used to get the Newton step before. You remember we had this model, right? And what we wanted is actually that pk is given as the minimizing argument over all possible p's of some model, m, which might depend on the current iteration, and which was making a model that is good in the neighborhood of xk of the current iterate. That was actually one interpretation of the Newton method that you might remember. Yeah, we used that notation. But this is not what the trust region method does. It actually adds an extra constraint to this. And it says, subject to the fact that the norm of the p, so the step size, in typically the 2 norm, but I will specify that not, so that we don't need that, is smaller than delta k. So you basically require that you minimize some model, which is usually a quadratic expansion of your objective function, subject to the fact that you want to stay in this circle. And how we solve it is another question. I will discuss it briefly only, but what you approximately solve this problem, you get a step, and you know this step will give you a descent direction if you make your radius small enough, because locally your model will be equal to your Taylor series up to first order, because you have the right gradient. So at some point it will surely give you descent when you make it small enough. Let me, for completeness, state what this model was. So this was a model which was based on the first order Taylor series exactly, plus an approximation of the second order term, which was using possibly a wrong Hessian matrix. It could also be the exact Hessian. It could be the second derivative. Then we got this Newton's method. It could be the Gauss-Newton Hessian, or it could be something that we get from these update procedures. It's very free. But this was the definition, and just to be absolutely sure, I just want to make sure that we are all on board. This model I could also write like this. It's exactly the same thing, but I just want to be sure that you are all on board with this notation, because it was confusing myself at some point. So this is actually the same. It's just more to write, and that's why I don't write it. But in the definition of this model, somehow I shift the origin of this p so that I can directly work with p instead of the difference. But this would be exactly the same thing. So I could also just say, I could also say xk plus 1 is equal to argmin of mk of x over all x subject to x minus xk smaller or equal to the trust region radius at k. So this would be, at least for the full step, for the steps, not for the null steps, but this would be the equivalent formulation. So calling it p or x is a matter of taste. It's completely equivalent. And what is now interesting is that this problem we know will have a solution because we have a compact set, this unit ball, and we have a continuous function, independent of curvature or anything. You remember, for these full-step Newton methods, we needed to have the fact that the bk was positive definite, because otherwise there could be negative curvature directions where your function goes to minus infinity. And because we just minimize this model without any constraint, these steps would not be defined if we have negative curvature. Now with this trust region constraint, the step would be defined. It would be maybe difficult to compute it, but it would be at least existing and defined. Yeah? And so one of the particular advantages of trust region methods is that they can deal with indefinite Hessians. Yeah, so you don't need to care so much about the positive definiteness of your Hessian. I should, on the other hand, say what we did is we replaced something which was easy, namely here we could just set the gradient to 0 and then we had a matrix inverse and we could just compute the step, by something which is more complicated. Because this is already an optimization problem. It has a quadratic objective, it has a circular constraint, but we would not immediately know, we could not write down the solution with some matrix inverse like that, right? So there is actually many different methods to approximately solve that, and I will come back to that in a minute. But the first point that I want to make is we need to have a rule how to adapt this radius, and this rule is completely intuitive, and I want to explain it to you first in words and then write it down as an algorithm. So what we want is basically that we go down. Yeah? And we know that as long as there is a gradient here, when we make really, really small steps, there is actually, if we go into, for example, the direction of the negative gradient, this term will be negative. This will be a bit positive, but it's getting smaller and smaller the smaller we make the radius. So the model will for sure actually be improving. The real function also gets similar and similar to the Taylor series, and this second order term will also be vanishing for the real function. So what you think is that the model and your real function will be, for very small regions, be identical, more or less. Actually, they correspond very much to the first order Taylor series, because the first order Taylor series is exactly in your model. So when you shrink your trust region radius enough, you are sure that your model is a good model in this region. Not outside, but inside the region. And so what the methods do is, as I said, they either do a full step, so then they are happy with this step, or they realize, no, this step is not acceptable, I need to make my radius smaller, and then I resolve in the next iteration the same problem with a smaller radius. That might give me a different direction, but at some point this direction will surely be a good one because I have a good model. And the algorithm has, so to say, two things to do. One is to decide if I accept a step or not. Yeah? And the other thing that it needs to do is I need to adapt this trust region size for the next iteration. So I can actually say this was a bad model, then I need to make my radius smaller, or it was a good model, then I can make my, if it was a very good model, then you think, oh, maybe I should make my radius bigger so that I allow bigger steps. And ultimately I would like that, of course I have very big trust regions, because the full Newton step, when I come close to a real solution, then you know if you have, for example, the exact Hessian, you would get this quadratic convergence, but only if your full Newton step is acceptable. And the full Newton step is actually a step where this trust region constraint doesn't matter because your minimum is anyway in the middle. So it's inside the region. So the two things we need to decide is, do we accept a step at all? And the second thing is, which trust region radius do we want in the next iteration? And they are treated a bit separately, but the reasoning for both is based on the same criterion, and this is a criterion which says if we have a good model or not a good model, and we define a quantity that we call trustworthiness of the model based on the prediction of what we think would be the decrease based on our model and the actual decrease that we got after testing this value. So we can actually compare two things. But let me just write this word, trustworthiness. It's the trustworthiness of your model, of the current model. It's the trustworthiness of a model at iteration K. So. And the trustworthiness is defined as the difference of two quantities. Actually, we call it rho k. So it's a real number that can be positive or negative. And this real number is defined to be the quotient of two quantities, namely of the actual decrease. I mean, our function, in the best case, it would actually go down. That means that this quantity would be a positive one, but it might be actually not, if we are unlucky. And we divide this by what our model prediction was saying for the same thing. And here, actually I can write either xk plus 1, or maybe I shouldn't do that. Actually, I should say xk plus pk, because I have the possibility that I don't accept the step, right? So if I do a null step, then it's not actually called xk plus 1. So I need to have the xk plus pk here. And so I divide the actual reduction with the predicted reduction. And sometimes you can also say this is the actual reduction divided by the predicted reduction. That's a funny way of writing it, but just to remember. So the actual reduction divided by the predicted actual reduction divided by the predicted reduction. And that's a crucial quantity that we use in these trust region methods in order to decide both things. If we want to enlarge or shrink our horizon, or to decide if we want to accept or not accept the step. Base two decisions on rho k, namely first acceptance or null step. So do we accept the step, or do we do a null step, or change of delta k? And what we can do with delta k is we can either shrink it, we can leave it like it was, or we can make it bigger, right? So these are the possibilities. And before we go through the algorithm, I want to discuss this property a little bit. So what does this rho actually mean? So if you have a rho which is 0, that means that this and this is the same. That means that you basically got no progress. Your trust region subproblem, you minimized approximately at least this function. So you started with something which was not the optimal point. This is the optimal point of the model. So this must definitely be better than that. So this thing is expected to be positive, and it is always positive as long as you have, a non-zero radius and you have a gradient. So this thing is anyway positive. So mk xk minus I can actually, mk xk plus pk is actually bigger than 0 if the gradient of f of xk is, I don't need that even, is non-equal to 0. Yeah, so a decent method of optimization will actually be able to improve inside any trust region when you have a gradient. When you just go a little bit in the gradient direction, you can improve it. So even if this was an approximate solution, you will improve it. But actually this thing, f of xk minus f of xk plus 1, is bigger than 0 if, this is trivial. So this is equivalent to f of xk plus 1 being smaller than f of xk, right? So that's what we would like. This is what we would really like, and what we think is actually that if these two quantities are similar, so if rho k is similar to 1, then we would say this was a good model, because what we predicted in reduction in our trust region with this model is similar to what actually happened after we tried. Here I should actually write plus pk, right? What we realized. Sorry, did I do something wrong? Here, right? Yeah, to be correct. That's what you say. Good. Yeah. Plus pk. Good. So if rho k is equal to 1, that means we have a good model. In principle, it can even be higher, right? So it could be higher than 1. That's not excluded. But anything that's maybe bigger than 3/4, we would say is a good thing, right? What is rho k being smaller or equal to 0 means that we have actually increase in the function value. So we would exactly have the contrary of this. Yeah, we would have a very bad model. And step must be rejected, right? Step would lead upwards, would increase f. So that would be not a good step for sure. So what we know is, roughly speaking, that 0 is the thing that we want definitely to avoid, and 1 is the thing that we would really like. And what we know is that when we make it small enough, that then the result, this trustworthiness, will become close to 1, because then the Taylor series will be coinciding anyway. And when we make it too big, there might be a danger that it gets too small. Yeah? So the intuition is clear. When this rho value is high, we might actually be confident and even enlarge the next trust region radius. If the rho value is small, we will actually better increase it to be more conservative at the next iteration. And independent, this is actually about the change. We should never accept a step where the rho is 0, but we could have some positive rho as a limit, which is a bit corresponding to this Amio sufficient decrease. So some value of rho from this moment on, we would accept a step. So these would be the two things, and a typical algorithm implementation would choose some parameters before, and I write down the algorithm 3, which is the trust region algorithm. This is the version that you find in the textbook of Nosedal and Wright, and I think it's a decent and nice version. And it has some inputs which are usually some of the parameters that you would need to decide up front. So one is a maximum radius that you would allow at any time, so you don't want to increase this to become too big. And maybe I should already say what we will, maybe I even explain it here. Sorry, not. So we could actually, acceptance or null step, we could make it based on the criterion that rho k is bigger than some quantity eta, yes or no, and this quantity eta should avoid that we get negative. So it should be a small positive number, and so eta is something that we will choose between 0 and 1/4. And this 1/4 is a bit arbitrary, of course, but it's what we will choose here. And we should also start with some delta 0. I mean, we need to have some starting value of our radius. We also need to start with some value x0, like before. For any Newton type method, we need to do that. And we need to specify some tolerance, which again I write with these 3-letter variables. That's a number like 10 to the minus 5, a small number that is giving the norm on the gradient that we want to have as a maximum. And the output is an approximate solution that I call here just x star. So it's not the mathematical solution, but it's the approximate solution that our algorithms give out. And it will actually iterate starting at 0. So I will actually not write it all down, but maybe first I will just write down what we need while this gradient at some iteration xk is bigger than the tolerance. You will do something, and that's where we start to improve, and then at some point we will end this loop, and we end it here, and I hope I have enough space in between, so we end the while here, use a Pascal-like notation here, and at the end, if this is okay, then we would actually say the last iterate that we got is actually just the solution that we output. So that would be the outline. I mean, that was like the algorithm before. But what do we do in between? We have, as I said, to do two things. We need to decide if we accept or if we do not accept a step. This is, let's say, the part that I will write here at the bottom. And what we do here is what I said already. We say if rho k is bigger than eta, then you accept the step. Because then the model is good enough, and we will have decrease, right? Because rho k bigger than eta. I didn't say that, but rho k bigger than eta means no, I had it here, right? So this is equivalent with decrease. So it means actually that we go down. If it's actually bigger than 0, even if this eta is something in between these two, then we would even accept a step only if it's really strictly bigger, making some progress. If this happens, then you just perform a step. Xk plus 1 is equal to xk plus pk. And else, you do no step. This is what we called a null step. So this is, let's say, already the most important part of our algorithm. We decide if we accept or if we don't accept a step. But if we didn't accept a step, then we should have at least increase the chance that next time we accept the step, right? So something needs to be changed. And the thing that needs to be changed if we did not accept the step is definitely that we make the trust region radius smaller. Okay, so what I need to squeeze in here is now two things actually, because we have three possibilities. Maybe I should just say adapt delta k. What you do is actually, first thing is you get pk from the solution of this problem. Tr sub and you also get, of course, rho k. You can compute it. So you actually compute the p, and then you also evaluate the rho. So these two things you need to get. And then the next thing is you adapt the size of the trust region radius. And what is already sure is that whenever you have something that you didn't accept, then of course you want to decrease the trust region radius. And here I need to zoom in because I don't have enough space. So what comes here, so to say, is the following. So if this rho k value was smaller than 1/4, and that's the same 1/4 that comes here, so it could be any other number, but I just choose here 1/4. So if it's smaller than 1/4, then I had a bad model. That's already a bad model. So I would say this is not a good model. I have a bad model. And then I reduce my trust region radius, and the typical choice is that, this is arbitrary if you do that or that. But anyway, what you do is you reduce your trust region radius by 1/4. So you make it really massively smaller in order to have next time higher chances to get a good step. But please note that depending on what choice of eta you had, you could have the situation that you accepted the step, but you still say it's a bad model and you adapted the radius. So next time you have already a smaller radius and hopefully then less danger of having to reject the step, because rejecting a step is expensive because you actually solve your trust region problem and then afterwards you say no. And so you want to avoid these rejections as much as possible. So this is this possibility to have a different eta than 1/4 allows you actually to sometimes accept a step but already take precaution for the next step and make the radius smaller, so that you want to actually control this rho k to be close to 1. Big. It should be relatively big. So then there's the other thing is you want to sometimes increase. And so you increase it actually in one situation only, namely when you have a good model and if you are at the boundary of your trust region. I mean, if you have a good model and your radius is so big that your solution is not at the boundary, you don't need to increase the boundary because it was not binding anyway. So you have this condition if the rho k is bigger than 3/4, so that was a good model. And also if the norm of pk is equal to the trust region radius at k. Then you have a good model but a too small radius. Yeah, then you should actually make your radius smaller, bigger, so then you increase it, take xk plus 1, and then the typical factor with which you increase it is actually 2 times delta k, so you're a bit less optimistic than you were pessimistic here, but that's just a detail, right? So you would actually make it bigger and bigger and bigger if you have a good model, but you want to avoid that this gets infinitely big. You never want that, so you actually choose the minimum of 2 and delta max. So that's like putting an upper limit that it cannot become incredibly big. This delta max is something you choose up front. And if nothing of the two comes, so basically if you had a model which was not particularly good but not particularly bad either, then this is where you are happy with the trust region radius, and then you just say my trust region radius should stay the same, and in the next step I will be of course at a different center point, but the radius of my model will be the same. And that's already the algorithm on the higher level. And if you want to visualize what happens with this algorithm in this multidimensional landscape, I want to do it as follows. So you can imagine, so to say, this situation. We have one iteration here. I just play a bit around. So what we have is an optimization landscape of the real system, which might be quite involved. So maybe we are here at the boundary of a banana valley, like last time, or like in one of the exercises, and maybe our minimum would be here. So just to have a nasty situation. We might start with a very big radius here. So this could be x0, and this could be, the radius could be delta 0. Yeah? So this was a very big radius. And then our model is based on some quadratic approximation of our function, and maybe the minimum of this quadratic function will be here. You test that first. Sorry, it's not here. It's because in the trust region it will be maybe here. You see it's already higher than this level line, so rho will be already negative here. So it cannot be accepted, and then it will be a null step. And you will actually say this is also x1, yeah, so it's the same. You don't do anything. x1 and x0 will be the same. But the trust region radius will be reduced because it was rejected. I mean, this was rejected, no step, and also it was a bad model, so we shrink the trust region radius. We shrink it by a factor of 1/2, a quarter. So now we have this radius, and this will be delta 1. It's still around the same point. And then our method will still use the same model. So this model was elliptic curves are level lines of quadratic models. And so it will have these curves. This would be the unconstrained minimum, but inside the circle, the minimum will be somewhere here. Yeah? And you see now probably this will be at least descent. Huh? And probably this is a step that we would accept. Yeah? So here would be, let's say, value x2. That we accept it. It is maybe, let's say, 0.5. So like maybe this trustworthiness is just 1/2. And if the trustworthiness is 1/2, then we say this was okay. We keep the same radius, but we now move it to this point. So what we will do at x2, we will take now the same radius, which turns out to be easy to draw because this was at the boundary, so it will be exactly the same circle, but moved. And I take a new model, that means I evaluate my gradient nu, and I evaluate maybe a second derivative nu, and then I have a new model which might have different level lines, and it gets too complicated if I draw now this new model inside the same graph, but this new model will be maybe giving me a good point here, and let's say this model is just giving me a point here in the middle of the radius, and it gives me improvement. Then I would actually just say here's x3, it gives me improvement. It's not binding, so there is no reason to increase my radius. Maybe it was even, but the descent was good enough, so I would probably have a situation where I would just keep the radius size, and now I'm here. Yeah, so I had a decent model, so I didn't increase my size. But it turned out that, I kept the same radius size again for one iteration. And maybe at the next time I got a better model somehow. It gives me now an iterate at the boundary, and it's still in this nice valley, so it's probably something which gets a good trustworthiness score, and it's binding at the boundary. So what would happen now? Let's say the trustworthiness, so this was xk, this is now x4, but we didn't do the step yet. But before we recenter, so to say, our trust region problem, when we have this binding thing and we have a very high score of rho, let's say rho is now merely 1, what will happen is that we are in the situation 2, where we increase. And so at this moment we would just say, okay, we accept of course the step, but we also increase the radius by a factor of 2. That's actually easy to draw again. So now we have this radius, and now we produce a new model based on this middle point here. Maybe this model looks like this, let's say, I don't know. And the next value of this model will be probably here. And then, unfortunately, this step is actually giving you uphill decrease, and then you realize, oh, this was too optimistic, then you have to shrink it again. So you can now play around, and what will happen is that you actually iteratively sometimes enlarge your radius, sometimes you make it smaller, and in the best case you accept most of the steps, but this one now, as I have drawn it, probably will be rejected again. So then you have to make it small again. That was too optimistic. Then you might get this point here. That is a good one, and then you keep this radius again, maybe for one iteration, and at some point you hopefully enlarge it, and maybe you are here, maybe you're getting large, and at the end you converge. Yeah? The last iterates, you would hope that your radius is bigger than your steps, and that you just make full steps, so to say. This is a sketch of how trust region methods behave. What we did not outline, and which I think I need to do in the next hour before we start the next topic, is how we compute the solutions of these sub-problems. And maybe, I think we should do it with some time, but that's basically the question we leave for after the break. But what I want to do now Switch off the camera, please. Yeah. Okay. As promised, I wanted to continue by explaining or by sketching how we can actually solve approximately these trust region methods and what people do in practice. So what this little section is about, it's called 9.5, and it's called the Cauchi-Point and how to solve the trust region subproblem. And this is only a sketch, but I decided that I would share with you one definition, and that is the definition of the so-called Cauchi-Point. And I wanted to start with a bit of motivation. So this trust region subproblem, it has the quadratic model, as I said, and it has this radius. This radius is usually the ball, 2 norm, could be also a maximum norm, then it would be a box, could be any norm actually. And some other norms are used, usually norm balls or norm boxes. This is what people usually use in implementations. There is, you will usually not expect that you solve this problem exactly, because that's also only an approximation of the original problem, so why should you spend so much time in solving that thing exactly? It's like exact line search, so why should you do that so exactly if you know it's anyway only one step towards the solution? This is again the same. You have a model which might be wrong, so don't spend all the effort in optimizing that perfectly. But because we want to prove stability later, we want to have some minimal things that make sure that this ensures convergence at the end. So just saying something that's approximately solving that is not enough. Yeah? So what people defined is they defined a point which is called the Cauchi-Point, which is already making progress. So to say, it's a bit like this, what Amio is like sufficient progress. And what then people say is we should always be better than the Cauchi-Point. Or maybe sometimes it's relaxed and they say we should be at least a factor of 1/2 as worse than the Cauchi-Point. But we should not become absolutely no progress in the model prediction. So the idea is that we want to solve the trust region subproblem. Yeah, so this thing that we call trust region sub approximately. But better than the Cauchi-Point. Okay. Which we still need to define. But the Cauchi-Point is like a reference. It should be better or at least as good than the Cauchi-Point, but maybe I should replace it, but at least as good. Yeah. Least as good as the Cauchi-Point, or at least a fraction of it. And what do I mean by at least a good? What is the measure of progress? So the Cauchi-Point will be something that I call PKC. Yeah? So that is a possible solution of the trust region problem, a feasible point which is improving the objective. Yeah? And so what we want is actually that the model prediction, it's only about the model, that the prediction that our step does, so the improvement of our step is this thing, right? So that was the improvement of our step, xk plus pk. And that improvement should be better than the improvement that we get with this Cauchi-Point, which I will define in a minute. Oh, this is because now I got the pitfall from my own notation. So this will be xk plus pk. Completely sorry for this. So here we have mk of xk, so that was the starting point. The Cauchi-Point will be an improvement of it. So this is expected to be smaller than this, yeah? And then there might be again some fraction which could be, I call it gamma because it's a bit related to this sufficient decrease in the Amio condition. So it has some similarity, but it's just arbitrary how to call it. A fraction of it, a fraction gamma of it. So it could be, so gamma should be smaller than 1, should be bigger than 0, and this is what we would, so to say, ensure. Yeah? So if this approximately, this should giving pk, yeah? So that it's at least as good as the Cauchi-Point. So this is, so to say, what you need to make sure, and the algorithms to solve it, they just need to have this condition, and of course, when we have this Cauchi-Point, I will define it in a minute, we could also just keep the Cauchi-Point and then just apply the Cauchi-Point all the time. This will not be a very good algorithm, but it would have global convergence at least. But of course we want to have something better, and that's why we still do something more. But what we will always do is we will first compute this Cauchi-Point, and so let us define first one thing, I call it the Cauchy direction. And I call it maybe DC. It's like a direction. It's and this is the solution of a problem which is very simple. It's the solution of the first order Taylor series of our function in the norm ball. Yeah? So it's actually the solution of dkc is equal to the argument that minimizes over all possible d's the first order Taylor series, which is the thing where our model was actually, so to say, relatively accurate. We leave out everything quadratic, subject to d in the same norm that we use, smaller than d, k. Yeah? This doesn't matter actually which radius we use as long as we take the same norm, because this is constant, this is linear, so this solution will always be at the boundary. Yeah? And if we have a circular truss region, it's even simpler, because if you have a circular truss region, you have your model and it's constant plus a linear thing. A linear thing will mean that your level lines will be also linear, and maybe the gradient points in this direction. Yeah, then this is going up and it's going down here, and the minimum will be definitely here, right? It will be then just the negative gradient for the circular things, right? So it's very simple to compute this thing for a circular thing. Yeah. So if this thing is equal to the 2 norm, if we take the Euclidean norm, then this gets then dk Cauchy direction is equal to what will it be? It will be the negative direction of the gradient f of xk. So it's like a gradient step, but scaled with the radius. So in this case, just to be sure, it would be then divided by the 2 norm of this thing and then multiplied with the step size. So then we would have, this would be the Cauchy direction. We just call it the Cauchy direction. It's not necessarily improving our model because it didn't have the quadratic term, but it's a direction which we can extremely easily compute by just looking at the gradient, and then we have this direction. That's why we introduce it. So it's the simplest thing that we can think of. And so it's not the Cauchi-Point yet, it's just the Cauchy direction. So what we have is basically a direction in which we want to look now. And we know that in the direction we will improve our, when we have the truss region small enough, or if the step length is small enough, then we would have actually an improvement in that direction. It's basically the gradient direction inside the truss region. I should say if we would use a box or another norm, then this direction might be slightly deviating from the gradient, but it's still easy to compute it. And I don't want to do it now. But based on this direction, I can now define the Cauchi-Point. That is this magic point that should always give us improvement in the model. So we want this to be positive. Huh? And the Cauchi-Point is actually it's basically using a line search in this direction on the trust region problem. Huh? So it's actually the Cauchi-Point is actually PKC. So the Cauchi-Point is given by TKC times DKC. Yeah? So this is the direction that we had multiplied with the step length. Yeah? Where the step length is obtained from optimizing the model that we have in the trust region subproblem only on this line. So it's actually doing a line search. With TKC being the argument that minimizes over all t. The following, namely the model of our trust region, xk, plus t times Cauchy direction, subject to that our t times the Cauchy direction should still be in the trust region. So what I wrote down is extremely intuitive, and it's easy to define it and also to compute it actually. So this was the linear model, so that was just to get a direction because this was cheap and easy. Now we look at the same direction, but we refine it already with this model that we use in the trust region subproblem, this model M, which contains also the quadratic term here. And we use, let's say I have this quadratic model, so we are still in the same region. We have already decided that this would be my direction DKC. Yeah? And now I don't have this linear model, but I know that because my first order Taylor series is exact at this point, so I know that locally it will actually be like this, but let's say our model is maybe a quadratic positive definite one, could be like this, I don't know, yeah? And so these would be my level lines, and here maybe it's my minimum, so could be like this, right? So this could be my model, my quadratic model. And then I minimize now along this line, and what will be this minimizer? It will be either the full step, that could be the smallest point, or it could be something in between. And this in between is something that I can also relatively easily compute, and maybe we want to do that once. We can try to derive what would be the possibilities here. Maybe we can do it. But the point before we do this detail is that we can, after we have found it, we have found a point which will definitely improve the model. Yeah? Because it's a direction where the model decreases, it's a descent direction, and we could also do no steps, so we could also, 0 is included, but we minimize along this direction, so it will be better than the starting point. As long as the gradient is non-zero, we will have some change, and that means that this is definitely positive. So this thing is always an improvement, it's always there, and what this whole improvement after the Cauchy-Point does, it can only improve more. That's, so to say, the idea. No, I will not do that now, because the time is getting over. I will just refer to the book of Nocedal and Wright. It's relatively easy. I say it in words. So what could happen is that you have, in the direction in which you want to go, you know the gradient is correct here, but you could have a quadratic which goes positively curved, like what I described here. And then this quadratic, you can easily find the minimizer of the quadratic on this line, and then this minimizer can be either inside the region, then you take that point, that's the minimum then, or it can be that for some reason this minimizer was outside, then of course it's not inside the trust region radius, then this point is the right answer. It could also be that you have negative curvature, so that you have, because I said at the beginning, B can also have some negative curvature. So if in the direction in which we look, this B turns out to have negative curvature, then it's even easier, because then I go down, and with negative curvature I will go down and more down, and then I will also be at the boundary. So basically there are two possibilities. Either it's here somewhere in the middle, or it's at the boundary. And there are two possibilities that lead to the boundary, and one possibility that leads to this interior. But anyway, this is how you would, so to say, compute the Cauchi-Point. After you have the Cauchi-Point, you're not done. You could actually just take that, but then you implement nothing else than a kind of gradient method, right? So then you just do steepest descent with some new way of adapting the step size. So what then the algorithms do is they take the Cauchi-Point itself, for example, and then they do some iterative linear algebra, things like conjugate gradient, for example, and they try to improve on that, only go down in the quadratic model. Or there's another variant that actually says, I have now computed my Cauchi-Point, and I can also compute my Newton point. This is the Newton point in this case. That would be the minimizer of my model. And then I go first to the Cauchi-Point, and then from the Cauchi-Point to the Newton point, and I find the best point on the way. Here it would be easy. The Newton point can only be better. Yeah? But if my Newton point would be outside this region, let's say, yeah, then I would go on this line, and I go towards the Newton point, but I stop when I hit the trust region radius, and then I take that one. This would make sure that if I can, and the Newton point is inside the trust region, at least I do the Newton point. And that's what you would like. And that is this thing, because you, so to say, first go to the Cauchi-Point, which is always possible, and then from the Cauchi-Point to the Newton point, because you do, so to say, two steps. This is called the dogleg method. Yeah? That's one variant. I should say that the dogleg method is only possible if, of course, this point exists, and that only exists if you have a positive definite Hessian, and then this is, of course, not always in all trust region implementations the case. But if you have this property, then you can also have a trust region instead of a line search with this trust region, with this method. Yeah, and then there are much more elaborate ways to solve these trust region subproblems. We don't want to go into details, but I just want to tell you it's usually based on this Cauchi-Point and an improvement of it. One thing I promised to Dimitris that I would still explain to you, and it's a pity, but it's actually helping for the exercise. And I just wanted to say that if you have a function from Rn to Rm, and you want to compute its Jacobian, and this function is just a black box computer code, then what you can use is actually, you can use the Jacobian, which is df by dx at some point x. This is what you would like to know. And in order to approximate it, you would actually use the definition of derivatives. We need that actually sometimes. And you would actually say what you would be interested in is very often this df dx at x in some direction p. So how does the function vary when you go in the direction p? And this thing is, of course, the same thing as d by dt of the function f of x plus t p. Do you agree? At t equals 0. So that is just chain rule, so to say. So you get some information about this derivative matrix in the direction p if you differentiate that thing. And this thing is, of course, the limit of t going to 0 of f of x plus tp minus f of x divided by t. Okay, this limit is something you can theoretically define, but if you have a computer function, you will actually just say this is approximately equal to f of x plus t something, or I call it maybe epsilon p minus f of x divided by epsilon with epsilon bigger than 0, but not 0. So you choose, for example, and very typically people choose epsilon to be the square root of the machine precision, which we call epsilon machine. That's a heuristic, I should say, but it's a good heuristic. For example, for double numbers, it's 10 to the minus 8, so it's a small perturbation, and you perturb your function, and what you will do is you take your computer code big F, you call it once at the point x, once at a point which perturbs in the direction p, you subtract them, you divide it by epsilon, and then you say this is an approximation for my product of the Jacobian with p. And if you repeat that for p going to be the unit vectors E1, and then you say P equal E2 and so on, yeah, where E1 is actually this thing, and E2 is this thing. Then consecutively you compute one column of the Jacobian after the other, and so you have to perturb your function n times in order to compute the complete Jacobian, and then you can actually evaluate f n plus 1 times, because you also need the center point, but you can store it. You don't need to recompute it again and again. Evaluate f n plus 1 times to get j at x. So to get the whole matrix J, you can do this. And this is what we call finite differences, and it's a way with which you can always compute a Jacobian of a computer evaluatable function, finite differences. And that is something that we can use whenever we don't know a better way to compute a Jacobian, as in this exercise at the moment. We will actually start next week a new chapter which is about derivatives and about much smarter ways to get these Jacobians. But at a moment I want you to know about this, and it's quite intuitive. So you choose just a small number, 10 to the minus 8, you perturb in each direction, you evaluate f again and again and again, and you use this vector difference divided by t in order to get one column of j. Okay, that way is finite differences. You will need it throughout your life, so it's a good thing to know this. Okay, I'm sorry we are a bit over time, but I still wish you a wonderful weekend. Thank you.